Welcome students. In this lecture we are going to discuss the two very important types of hypothesis tests, which are the one sample and two sample t-tests. These are very important topics from statistical inference, and they need to be understood quite well because many things, many advanced topics require their good understanding. So let's start with it. Firstly, we should know what are the t-tests. The t-tests or the t-tests of means are parametric type of hypothesis tests. By parametric type of tests, we mean this thing that these are the type of tests that depend upon certain assumptions, and those assumptions must be satisfied, must be true. Then we can actually perform these tests. The fundamental assumption which is used or which is to be true to perform these one sample and one sample t-test of means and two sample t-test of means is that our samples or the samples are taken from sampling distribution of means which is normally distributed. Now what actually happens is this, that let me give you an overview of the scenario, that we would be provided in the t-test of means, we would be provided either a single sample from the population or multiple samples from the populations, and we would be required to test something about the population mean. Now, we must understand this thing very, very carefully, that the sample that is given to us is always part of the sampling distribution of mean, right? And remember this thing, that the sampling distribution of mean is the only handle, is the only key, is the only way to understand or to hypothesize or to view about the population. And we also know this thing from our previous lectures, that the sampling distribution of means are always normally distributed. Their central values is the population mean, and they have the standard deviation which is called the standard error of mean. These are the things that we understood from the central limit theorem. So this assumption is always taken into consideration when we are performing one sample t-test of means and two sample t-test of means. We won't be checking this assumption while we are performing these t-tests, but we assume that it is true that the samples are taken from the sampling distribution of means, right? And since we are performing the t-test, not the z-test, so the second thing that would always come into play in when we are confronting these questions would be that we won't be provided with the population standard deviation, or a sample size would be less than 30, because in only these two cases we use the t scores or the t distributions. So that's why the t test nomenclature is given to the test that we are going to perform over here. Hence, the equations formulae used here follow those that we studied in central limit theorem, especially the t-score equations in estimation of single mean and the estimation of differences of means. So we should remember those equations, because those concepts that we discussed in those lectures, in the CLT lectures and in the estimation of mean and the estimation of difference of means, would be quite a lot used over here. The t-tests are the hypothesis tests which are performed to test about the population mean or means using given sample or samples. So we can have one sample or we can have multiple samples when population standard deviation is unknown and or sample size is less than 30. We have two types of t-test of means: one sample t-test of mean and two samples t-test of means. Firstly, we'll see what are these one sample and two sample t-test of mean and means, and then we will look into their proper scenarios. So one sample t-test of mean, this hypothesis test is used when we are provided some general belief about the population mean, and we tend to test it to be true or not using a single sample. So the scenario would be that we would be given a general fact about the population mean, and uh, we would be testing that whether that general fact is actually true or different or not. The second is the two sample t-test of means. It has basically two types. One is the independent means and the second is the dependent means or the paired samples. And these are exactly the same two types that we discussed in the differences of the estimation of means as well. So all the theory, the concepts, the conceptual understanding that we discussed over there for the two sample, for the estimation of the differences of means could be applied over here as well. So again, I would recommend you this thing that before proceeding with this lecture, you should have some good understanding, a good grasp of the estimation of the difference of means. So independent means two sample t-test of means, this hypothesis test is used when we are provided two separate samples from the two separate populations, and it is required to test if there is difference between the two, or if one is greater than the other, or if one is lesser than the other. This test is performed by using two samples data from the two different populations. Dependent means two sample t-test. In this test, we are provided, basically, the concept is again the same that we discussed in the estimation of the differences of mean. This hypothesis test is used when we are provided two subpopulations taken from one single population, and it is required to test if there is difference or between the two subpopulations, or if one is greater than the other, or if one is lesser than the other. This test is performed by using two samples data from the two subpopulations and then creating a new differences sample. Now, few things regarding the null and the alternate or alternative hypothesis we would discuss over here. Although we discussed these null and the alternate hypothesis in quite much detail in our previous lecture of the hypothesis testing theory, but few things need to be catered over here as well. So, firstly, about the null hypothesis. It is to be noted that the H naught or the null hypothesis is only defined inside its specified confidence interval region. Our scenario would be that we would be in the questions, you would see this thing that we would be given a null statement, or a true fact about the pop, or a true supposed to be fact about the population, which is supposed to be true, and with some confidence interval. And the understanding is this, that 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 fact is considered to be true only within that confidence interval, and outside it is not considered to be true. So basically it means this thing that in the null hypothesis, the null hypothesis only exists, or the population of the null hypothesis only exists within the confidence interval region, right? And outside the confidence interval region is not part of the H naught or the null hypothesis. This outside region is also called as the region of rejection. And we should remember this thing when we are discussing about the hypothesis testing practical examples. Likewise, there are a few things related to the alternate or alternative hypothesis as well. Remember this thing that the alternate or alternative hypotheses are always made against the null hypothesis. They are always made to nullify the null hypothesis. So in research, there are basically three types of making statements against the null hypothesis. One is called the upper tailed, second one is called the lower tailed, and third one is called the two tailed. And what happens in these, let's see this thing, the research or alternative hypothesis can take any of the three forms, and the researcher or the investigator might believe that the parameter has increased, decreased, or changed. When he believes that the parameter has increased as compared to the one that is given to us, then it's basically called the upper tailed test. And when he believes that the parameter has decreased, then this is called the lower tail test. And when he believes that it has changed, it can be either increase or decrease, both would be okay, then this is basically called a two-tailed test, right? So upper tail test is a one-tail test, lower tail test is also a one-tail test, and two-tailed test is basically a two-tail test. Uh, in the upper tail test, in this test, alternate hypothesis, which is basically the HA, is tested for the case which is greater than H naught case. In the lower tail test, which is again a one tail test, In this hypothesis testing, HA is tested for lesser than H naught case, and in the two-tailed test, the H naught is tested to be different from the H naught case. So let's see all these things pictorially. Over here, we have basically a sampling distribution of means for H naught population. Again, remember this thing. I would recall this thing again because this is a very important concept. When we talk about the population, we actually don't know about it. That's why we do the statistical inference. That's why we take the samples and analyze those samples and try to generalize the results onto the population. But what we know about the population is this, that by central limit theorem, the sampling distribution of mean which is made out of the population is always normally distributed. So that is why in the texts, in the literature, you would see this thing that occasionally, many times we basically represent the populations with a normal distribution. And the reason for this is only because the sampling distribution of means is actually normally distributed. So that's why we do it. So over here we have such a case that the sampling distribution of means for H naught population is shown, which is normally distributed, and we can see this thing that what is an upper tail test for this case. So suppose we have some H naught, and the mean of this H naught is definitely the mean that's defined by this H naught is definitely in the center, because at the center of the normal distribution shows the population mean, and it has some confidence interval as well. And what we mean by this is this, that within this confidence interval, we are sure that the H naught population is present within it. But outside this confidence interval, we take it in this way, that this outside region is not part of the null hypothesis population. So we can see this thing that we have the critical value over here. The critical value which is the boundary value between the no rejection region and the rejection region is here, right? So this critical value, on the right hand side we have the rejection region, and on the left hand side of this critical t value we have the no rejection region. Now, what is this critical value? This critical value is basically obtained from the confidence interval, right? And it is also the level of significance. Okay, so you can take it in this way, that for example we had 90% confidence interval, then the t value corresponding to this 90% confidence interval for one tail case would be this critical value. And on the right hand side, we have the type 1 error region or the alpha region. And on the left hand side of this critical T, we have the H naught region, right? And also note this thing, that this is the and how this type 1 error comes into play over here. Because remember, what is the type 1 error? Type 1 error was the error which shows that we are rejecting the H naught when it is actually true, when it is actually present. This is a false positive error as well, and it is a type 1 error as well. Both are the synonymous terms. So we can see this thing, that we would be rejecting the H naught, right, when we have something in the alpha region, right? And if we are rejecting H naught when we have something in the alpha region, then the error would come into play if, for example, this alpha was very much high in area, then definitely we would be rejecting the H naught, right, because of the high alpha value. But probably we are rejecting it falsely, although the H naught was true, right? So the lower this alpha would be, the better would be the case. The lower would be the probability of rejecting the H naught when it is actually true. So we can also see this thing, that how this alpha comes into play. And if you want to actually see that the visualization of the how the significance level changes the area of alpha, then we had a video for it, and I would recommend you again that go and view that video of the hypothesis testing, where we simulated this, how this alpha varies with the change of the significance levels. The second case is for the lower tail test. Over here again we have the sampling distribution of means for the H naught population, and we can see that we have some critical t value over here again, and this is on the left hand side, right? And this critical t value shows that on the right of this critical value we have the region of H naught, and on the left of this critical value we have the rejection region, right? So whatever comes on the right hand side of this critical value would be taken as part of the H naught, and whatever comes on the left hand side of this critical t value would be taken as part of no H naught. belonging to some other population, and that population definitely would be of alternative hypothesis or experimental or research hypothesis. And again, we can see this alpha is defined over here, right? So increasing in alpha would basically increase the type 1 error rate, the error of rejecting the H naught, while decreasing this alpha would decrease the type 1 error rate, that is, would decrease the probability of rejecting the H naught. Just it was the case over here as well. So if we increase this alpha, it would increase the probability of rejecting H naught, and if we decrease the alpha, it would decrease the probability of rejecting H naught. Like we can see this thing in the simulation over here as well, right? So if we have this marker taken as the level of significance, so if we basically move it on the right hand side, what we are doing is basically we are reducing this alpha region, and in doing it in this way, we are basically decreasing the probability of rejecting the H naught. But if I slide it on the left hand side, right, so what we are doing is we are basically, in this way, we are basically increasing this alpha region. And when we are increasing this alpha region, what we are doing, we are increasing of rejecting the H naught, because the greater this region is, the more would be the rejection region, the more would be that region which is not part of H naught. So that's how this type 1 error comes into play. And wherever the marker would be, right, wherever this marker would be, it would be defined by the critical T value. So that's the purpose of the critical T value. It is a level of significance. And that's always taken from the T table. So that was about the upper tail and the lower tail t-tests. And next comes the two tail. In the two tail, as we can see this thing, that in two tails we are basically using both the tails of the t distribution. And again, this is the same distribution, which is the sampling distribution of H naught. So we have two critical t values over here, one on the right hand side and one on the left hand side of the t0, the central point. The right hand side is as shown over here, has the on the region on the right of it is alpha by 2, and the minus, and it is a positive t value, or let's say, better put it in this way, it's a positive critical t value. And on the left hand side we have a negative critical t value, and the region on the left hand side of it is alpha by 2, because total overall rejection region is alpha, and when it's divided by 2, then it becomes alpha by 2. So you can see this thing in all these three figures, that since this critical T value defines alpha region, so I mean, most often in the textbooks and the literature, you would see that this critical T is symbolized by T alpha or T alpha by 2. It's symbolized by T alpha in upper tail and lower tail cases, and by plus T alpha by 2 and minus T alpha by 2 in the two tail cases. So it would be minus T alpha in the lower tail case, pardon me. So we sometimes represent it with TC, but we can also represent it with T alpha or T alpha by 2. All are okay. Now let's understand some basic skeleton procedures for the hypothesis testing. If we remember, my dear students, if you remember these skeleton procedures, the format, the template, then it would be very easy for us to understand that how these hypothesis tests take place. So the first hypothesis testing procedure that we will be discussing is about the one tail, and second we will discuss about the two tail. But for both the cases, let's see what are the basic procedures. So following are some common steps to be followed in any of the hypothesis testing. The first step is this, that we should explicitly write down our null hypothesis statements and the alternative hypothesis statements. Now this is a very, very important thing, that before starting our research or before starting our data analysis, we should explicitly know that what are the hypotheses. I mean, which hypothesis is to be tested against which hypothesis. That is the H naught and the HA. The second step is find the sample statistics. The sample that we are giving, we should know the basic parameters of it, like its sample size, its mean value, its standard deviation, variance, and definitely then its SEM, or the standard error of the mean. The third step is finding the t statistics. Now this includes finding the t value from the given sample statistics. The equations or the formula that we used are basically the same that we discussed in the central limit theorem. That is, the equation that would be used would be followed from the idea or from the properties of the central limit theorem. And that's why we say that this is a parametric test, because we are using the equations and the formulae that we discuss in the central limit theorem. The t statistic or the t value that we find in this third step is also denoted by ts, t with the subscript of s. And the fourth step is finding the critical t value. This is obtained from the t table, and for finding the critical t value we should know the degree of freedom, and we should know the confidence interval, and more importantly we should know that whether it is a one tail test or a two tail test, because we, as we know from the t table, we have the confidence intervals or the significance levels for both one tail and two tail. So we should know that which type of test we are basically performing. The fifth step is to compare to see if the t statistic is different from the critical t value. It can be greater, it can be lesser, or it can be just different from it. And that depends basically upon our alternative hypothesis, that what we are actually trying to find. Now, the last step is the sixth step, which is depending upon the previous step number five. We have to decide to reject or to not reject our null hypothesis. If TS is in the rejection region, then we reject the null hypothesis, otherwise not. Now, this is a very important point to understand. Now, just to understand this idea, if we go back into this figure, like for example, we take the example of the two tail t-test, we have some critical t value as we can see, and that would be defined by the table that we the t table that we just discussed. Now definitely after having this sample we would get some t statistic, and that we call the ts. Now this ts would be lying somewhere on this horizontal axis. Now basically it can be lying on the left, either on the left hand side of the plus tc or on the right hand side of the plus tc, right? So if it is coming on the right hand side of plus TC, or it is coming on the left hand side of minus TC, then definitely it would mean that that T value is in the part of the rejection region. And what does it mean? It means that our sample is in the part of the rejection region. And what does it mean? It means that our sample does not belong to the population of H naught. Rather, it belongs to the population of alternative hypothesis. And when this happens, we would have enough confidence, and that we call basically the enough statistical confidence that we can reject the null hypothesis, right? So it's a very important step to understand this last step number six, that depending that whether this TS is lying in the rejection region or in the no rejection region, we decide that whether we have to reject the null hypothesis or not reject the null hypothesis respectively. Now let's understand these steps in terms of the one sample t-test of mean. So as we discussed, we have to formulate our H naught and HA. Now we should know this thing, that the null hypotheses are always standard statements. Like for example, over here we are discussing one sample and two sample t-test. The null hypothesis are standard statements for it. Later on, when we will be discussing about ANOVA or correlations and regressions, then over there again the null hypothesis would be the standard statements. We cannot change those statements. They are standard statements. Like for example, for one sample t-test, what is the null hypothesis? The null hypothesis is basically some given general fact about the population mean. That is what we take the null hypothesis, right? And the alternative hypothesis could be either we are testing that actually the mean is lesser than mu naught, or the mean is greater than mu naught, or the mean is just not equals to mu naught. Like alternative hypothesis mean is less than, greater than, or not equals to mu naught. So you can also put it in this way. Find sample statistics, as we discussed in the previous step. The sample that we would be given, we would just given one sample. It's a one sample t-test because we are just given one sample to test against the population, to generalize against the population. So note this thing as well. In a one sample t-test, we would be just given one sample to test anything about the population. So we should know that the statistics of that sample, like its sample size, its mean, and the standard error of the mean. The third step is finding the t statistics. Now, in the previous slide, we said about the t statistics. Now, the equation that we use in a one sample t test is basically to find the t value is basically ts equals to x bar minus mu naught upon s upon root n. We should know the format of this equation. Firstly, you can see that you have confronted this equation previously as well. And where did we confront this equation? We learned about this equation using the central limit theorem. So this equation is basically the product or the outcome of the central limit theorem, or you can also put it the other way around, that this equation shows the existence of the central limit theorem. So that's why we said that this is a parametric testing, and it uses the assumptions that the central limit theorem is true when we are performing the t-test. So the second thing to note over here, the numerator of this equation is x bar minus mu naught, right? So it's basically the difference between the sample mean and the population mean defined by the null hypothesis. So note this thing, that it is the difference between the sample mean and the population mean defined by the null hypothesis, right? We are trying to find the difference between the two. The more the difference between the two, the more our sample would be deviated from the null hypothesis. Note this thing. And the lesser the difference between the two, the less our sample would be deviated from the null hypothesis. And the more it is deviated from the null hypothesis, the more is the probability that it is not part of the null hypothesis population. And the less it is deviated, the less would be the probability that it is not part of the null hypothesis population. The denominator is basically s upon root n, which is the standard error of mean. Remember, this s upon root n also shows the sampling variations, right? And these sampling variations can be reduced by increasing the sample size. So it is basically the equation which can be related to something like signal to noise ratio. The numerator is the signal and the denominator is the noise. The higher the denominator would be, right, the lesser would be the t value, and the lesser would be the difficult it would be to identify the effect, right? And the lesser the denominator would be, the higher would be the t value. And remember this thing, the higher the t value is, right, the more it is away from the null hypothesis. And definitely it would show this thing that our alternative hypothesis would have the higher probability to become true, or the effect that we are trying to find can be easily determined. So it's this equation can also be related to something like signal to noise ratio. We are trying to identify or explore a signal in the presence of the noise, something like this. The fourth step is the finding the critical t value, and that would be determined by the table as we just discussed in the previous slide. And then the fifth step is again to compare this ts with the critical t, and depending that whether our ts is lying in the rejection region or not rejection region, we can reject or not reject the null hypothesis respectively. Now the procedure for the two sample t-test. The null hypothesis and alternative hypothesis statements are the first step to write. So what is a null hypothesis statement in a two sample t-test? It's again a standard statement, and we start our analysis by assuming or by taking into consideration of the null hypothesis that actually there is no difference between the two populations. Now note this thing, that in a two sample t-test, as we discussed just previously in the introduction, that we would be given two samples from two populations, right? So one population would be mu1 and the second population would be mu2. And we make our null hypothesis statement in such a way that actually there is no difference between the two populations. They are the same. When they are the same, then their means would be the same as well. So the null hypothesis statement is mu1 is equals to mu2, or you can also put it in this way that mu1 minus mu2 is basically equals to 0. Mathematically, both are correct. And the alternative statement is this, that either mu1 is less than mu2, or mu1 is greater than mu2, or mu1 is not equals to mu2. When we say that mu1 is less than mu2, then this can also be stated like mu1 minus mu2 is less than 0. Mathematically, both are correct. When we say that mu1 is greater than mu2, then this can also be put it in this way, that mu1 minus mu2 would be greater than 0. Definitely, when a smaller number is subtracted from a higher number, the result is greater than 0. And when a smaller number is subtracted, when a higher number, a greater number is subtracted from a smaller number, then the result is definitely less than 0. And the third type of alternative hypothesis we can have is mu1 is just not equals to mu2. That is not different from each other. Now finding the sample statistics, in terms of sample statistics, since we would be given or provided two samples from two populations, we should have the sample sizes of each sample. We should have the means of each sample, like x1 bar and x2 bar, and sample sizes like capital N1 and capital N2. And we should have the SEMs of both the samples. taken, I mean, considering that they are part of the sampling distribution of means, so definitely should have the standard error of means of both of them, which is S1 upon root N1 for sample 1 and S2 upon root N2 for sample 2. Then next comes the step of finding the t statistics. Now t statistics is basically x1 bar minus x2 bar minus mu1 minus mu2 under root S1 square upon capital N1 plus S2 square upon capital N2. A very similar equation we discussed in the estimation of the differences of mean election. And I would recommend you that in order to better understand this equation, it would be much better that if you go through that lecture again, if you forget the things that how this equation has appeared. It is actually a rearrangement of that equation where we saw that what is mu1 minus mu2, right? So just a rearrangement of the things. The thing to be noted over here is this: as we compare it with the one sample t-test, the t-statistics was x bar minus mu naught in the numerator. So there was some sample mean minus the population mean defined by the null hypothesis. And the same thing is happening over here. We have some sample mean x1 bar minus x2 bar would give something like x3 bar, right? A new sample mean. So it's a sample mean thing minus mu1 minus mu2. Mu1 minus mu2, if you note this thing, is the same value that we got from the null hypothesis statement. And in the denominator, we have s1 square upon caps n1 plus s2 square upon caps n2 and under root. You remember this thing that this is the standard error of the mean when two populations are subtracted or added. So this is again the SEM thing. And we can see from the null hypothesis statement that mu1 minus mu2 is basically equals to 0. So this equation can be modified into this thing. Now we can have two cases. Besides that mu1 minus mu2 can be 0, we also know this thing from again our lecture discussion on estimation of the differences of mean, that we can have two cases further. Either we can have the case that the two variances of the two samples are same, or we can have the case that the two variances of the two samples are different. So we can have the case of equal variances and unequal variances. If it is the case of equal variance, then TS can be written as x1 bar minus x2 bar upon SP under root 1 upon N1 plus 1 upon N2. And what is SP? Do you remember this thing? SP is the pooled standard deviation. It is standard deviation that is created by grouping the standard deviations from the two samples when it is the case of equal variances. And if it is the case of unequal variance, then TS is given by x1 bar minus x2 bar upon under root s1 square upon caps n1 plus s2 square upon caps n2. Again, note this thing that these two equations, this mu1 minus mu2 factor that we wrote over here is basically equals to 0 because in the null hypothesis statement it is 0. Next, the fourth step is finding the critical t-value that is taken from the table by using the degree of freedom and Ci, which is the confidence interval. But again, note that for the equal variance case, the df is n1 plus n2 minus 2. That is sum of the sample sizes from two samples minus 2. And the degree of freedom for the unequal variance case is given by this big formula, which is s1 square upon caps n1 plus s2 square upon caps n2, the whole square of it, divided by 1 upon n1 minus 1 s1 square upon n1 square whole square plus 1 upon n2 minus 1 s2 square upon n2 whole square. So it's the weirdo looking formula. It looks like something quite scary, but it's, believe me, it's really easy to work with. We just have to plug in the values and we can easily get the answer for the DF. The fifth step is comparing the TS with the critical T value. We can have either the case that it is less than, greater than, or equal to, or not equal to, depending upon our alternative hypothesis. And the last step is again that whether if our TS is lying in the region of rejection or not region of rejection, which is given by the step number 5. So depending on step number 5, we can reject or not reject the null hypothesis depending that whether our TS is lying in the region of rejection or region of no rejection, right? So that's how we basically work with these one sample t-test and two sample t-tests. And there's one more case remaining, which is the case of the dependent means. So let's go through that case again, that case as well, just like we discussed these cases over here. So procedure for two sample t-test of means again, but this time it is the dependent means two sample t-test. And remember what's a dependent means? It is the case when we take two populations from one single population. Or to put it in a better way, we create two subpopulations from one single population. So it's just like this thing that we have basically classified or categorized our population into two classes or two categories, and we assume that there are two new populations, and we take samples from the from those two populations, and then we analyze it. In the lecture of estimation of the differences of mean, we learned this thing that how we analyze them. What we actually do is this, that we take from the two samples that we take from two subpopulations, we create a new differences data set, and we find a mean that is basically written as XD, and then we find the mean of it and the standard deviation of it, and then we analyze it. So first, let's see how we write the null hypothesis and the alternate hypothesis statements. The null hypothesis is mu d is equals to 0. What is mu d? It is the population mean of the differences. It is the population mean of the differences data set. The differences data set that we create by finding the subtraction or by finding the differences of the two samples is assumed that it is part of the new population, which is basically called the differences population, and it is written by the mean of it is written by mu d. So the null hypothesis statement is this, that mu d is equals to 0, which basically means that there is no difference between the two subpopulations. And the alternate hypothesis statement is this, that mu d can be greater than 0, or it can be less than 0, or it can be just not equals to 0. Remember that any one of them would be present over there. Then the next step is finding the sample statistics. So that it means we need to find the XD bar, the mean of the differences data set, the sample size of the XD sample, that is the new differences data set sample size, and the standard error of the mean, which is the SD upon root n, where SD is the standard deviation of the new differences data set. Then the finding the t statistics are given by XD bar minus mu d upon SD upon root n, and we know that mu d is equals to 0. So it shrinks down into XD bar upon SD upon root n, which is again the similar formula that we discussed in our previous slides taken from the central limit theorem. Then the fourth step is finding the critical t value. That is finding the t value from the t table using the confidence interval of our test and the degree of freedom, which is n minus 1 in this case. Fifth step is comparing ts with the tc value, whether it is greater than, lesser than, or equal to or not equal to, depending upon alternative hypothesis statement. And the sixth step is, depending on step number 5, we have to decide to reject or not reject the null hypothesis. Remember, if TS is lying in the region of rejection, then we reject the H naught, otherwise not. So this was the basics of the one sample and two sample t-test. In the later examples, in the later lectures, we would take the examples, practical examples, to actually learn and see this thing, that the procedures that we have learned in this lecture, how they are practically used. I would again say that if you have any problems, any confusions, any queries regarding this lecture, then write down in the comments, and then I will get back to you to answer your questions. So thank you very much. Stay healthy, stay safe.